So I'm Sean Myers. I'm with House of Brick Technologies. I'm a consultant. I'm a database administrator. I focus on virtualizing large SQL servers. So a lot of stuff we talk about today is going to be regarding, well, large SQL servers and how we have NUMA issues. I've been with House of Brick for about 6 years. I've been working with databases for a very long time, and with SQL Server specifically since 1996.
Hi everyone, I'm Rob Gerard. I'm a principal TME with Tintri. I've been with Tintri about 3.5 years. Check us out in booth 429, and there's my marketing plug. Anyway, been in IT for 20 years now, I guess. Got drunk on the VMware Kool-Aid back in 2005 with my first VCP and been pretty hooked on it ever since. Get an opportunity in tech marketing to do a lot of lab work, a lot of best practices, and sessions like this are great because when we put in for call for papers, if it gets accepted, then I can actually spend the time doing a lot of the lab work that you'd love to do, but you're too busy putting out fires or keeping the lights on or building new stuff. So hopefully this is of value to you.
And we're nice. We like to do a 2-minute session. And if you can leave afterwards, but then if you want to know more, stay, and we can get through all the reasons why we cover all the stuff here. So the short version, use a green line config. And we cover what a green line config is. There's a blog post by Mark A. from VMware to discuss all that. Use those for your underlying performance. Leave hot add CPU off. On your virtual machine, there's 2 settings there. The auto size once false and auto size true. They're set to true kind of stuff. And 6.5, it's defaulted to true. It's actually set correctly now. Otherwise, leave everything else alone and it's going to be fine. If you want to know why we talk about that, you can stick around. If that's all you needed, you're free to go find a new session and learn some more stuff.
No takers? Okay. So Sean and I met back in April of 2015. VMware and Tintri did this SQL expert workshop. So they took in 15, I think it was 15 or 17 of the top DBAs across the country for a very intensive 3-4 day workshop. There was some Tintri storage underneath, and there was compute on top. And everybody, the DBAs in the room were just banging away on it. Everybody was having a good time. And there was a lot of back and forth conversations between VMware and the DBAs so that things could move in a direction that make the DBAs happy, make the virtual infrastructure admins happy. And so one of the topics that came up in that was NUMA, and there was a bunch of other things we discussed. And I wanted to put in a call for papers for VMworld to speak. So I asked Sean if he'd co-present with me. In the room, he definitely knows his SQL freaking wicked awesome. But beyond that, he's got a virtual first mentality. I thought, hey, this would be a lot of fun to do. So we put it in, ended up getting a small little group session, group discussion of 50 people. A couple years ago, did a couple of those, did it on this VNUMA, got a lot of feedback, then reiterated it, presented this last year in US and Europe, and we've been just kind of refining it as we go. We get feedback while we're presenting. You know, we don't know this at the time, but it turns out that the developers that actually wrote the stuff will be sitting in the room and they'll come afterwards. So by putting this stuff out there, we've had the benefit of getting a lot of feedback on it. So we're hoping this will be a valuable session for you.
And if you've seen it in the past, it's actually been updated for 6.5 and some things that VMware has changed internally on some of the patches too. So agenda we're going to cover basically, well, you can read through it, we'll get there. But explaining NUMA, how it works, and what we did in our testing. So just some background information on NUMA. So back actually, before we had NUMA, we had symmetrical multiprocessing, or SMP, which was basically one processor, or a group of processors, and one memory controller and all your memory. That worked great and everything was fine except for we ran into bus problems. The access to the bus became the bottleneck, so your CPU was all jammed up trying to get to access to memory. Things would slow down. So they came up with NUMA. Oops, sorry. Go back one. Which is non-uniform memory access. Basically what it means is they now created 2 memory controllers, one for each processor, or 4, it depends upon how many sockets you had. And they broke the systems up. This allowed us to have additional buses for each system so memory access could be fine.
So I'm just going to interrupt for a sec. I've noticed a lot of people taking pictures. Feel free to, but also we can distribute this by PDF afterwards. It'll also be on demand, I believe. But if you want the PDF after the session, come on up, give us your business card, and just write NUMA on it, and we'll get that out to you. Also, feel free to ask questions along the way. There's microphones. Just come up to them. If it's something we're going to cover, we'll just let you know, but feel free to interact with us the whole time.
And if you have a question you want to ask later on too, we're around. Come see us at the the VMware Customer Appreciation Party. Come and say hi, and we'll talk all kinds of stuff. We like to sit around, sip beer, and talk technical stuff all the time. All right, so back where I was. So at the end of the day, now we have broken my memory banks into the two groups or 4 groups, depending on how many NUMA nodes I have. And I have a memory locality. So the local memory is faster than the remote memory, which is what we're going to walk through a lot of. So AMD and Intel have approached NUMA differently. And I have not fully played with the new AMD technology, so I don't know their NUMA topology. I'm assuming it's the same, but I don't know. But currently, AMD actually has 2 NUMA nodes per processor. And so what it is, you get in with a 2-socket box, you're going to have 4 memory controllers and 4 banks of memory. So if you happen to have 64 gig of memory in the server, you usually got 4 groups of 16, or 640 gig would be 160s. Intel, you have 1 memory controller per processor, basically, and you see on a 4-socket box, you're going to have 4 memory controllers. Also notice the lines in between there. Those are what they call QPI links. So if you're actually reading the Intel specs and it says QPI link, it's basically a quick path interconnect. It's how fast my memory can reach each other from different nodes. The first earlier versions before on the QPI links, there was only 1 or 2 of them, and you had path issues, so you'd have to do a double hop on a 4-socket box to get to your memory. Now they've did a mesh topology across it, so when you have like an 8-socket box, everything is integrated. So Intel's also introduced a new technology as of Haswell v3, which is called cluster on die. So cluster on die is, we found out with the bus speeds again and having processor cores that are greater than, say, 20 nowadays, we have memory access problems again. So what cluster on die does, it now breaks up a single processor into multiple NUMA nodes, i.e. like AMD, and it depends upon how many sockets there is. They've added lots in this, and then with that, they've changed the microcode at the processor level. And there's 3 different flavors of it, basically cluster on die, early snoop, and home snoop. And it's all about how you keep the L1 and L2 cache coherency information close to the processor to access your memory. The good news is it's awesome. The bad news is nobody knows what works best for each workload yet. Currently, VMware says you should leave it at OEM default, meaning however your server vendor sets it, leave it that way. If your server vendor has a best practices guide, i.e. HP or Dell, or UCS, kind of cyclical UCS, they might have a guide that says switch it to this for this workload, leave it for this workload. There's not a lot of good information from them yet. They're starting to talk more about it. Intel has a white paper that I don't know if I was supposed to get or not because I found it on a link on one of their forum sites, but I can't find it on their regular site, and no one from Intel wants to give me a copy of it again. But I still have it. But they showed some of their testing. It shows a 35% increase on a certain benchmark when you change the Snoop models, for that. Which one works the best is going to vary by workload because they did 15 different benchmarks in that white paper, and only one of them had a drastic difference. Most were only between 2 and 5%. So pNUMA versus vNUMA. So we say NUMA and pNUMA and vNUMA, and sometimes we want to make sure we don't confuse things to you. So pNUMA, when we say that, or we say just NUMA, we're typically talking about the physical NUMA architecture of the hardware. vNUMA is the virtualized abstraction of that being presented to the guest OS. So VMware has vNUMA, and it presents that to your guest OS. And Windows, Linux, and SQL Server have all been NUMA aware for a very, very long time. Oracle is also NUMA aware, but they tend to say turn it off. I haven't had enough time to go test to see if I can make performances work better that way or not. Soft NUMA. Inside of SQL Server, they had a construct called soft NUMA. What this is, well, in the old days, the original version of it was, it allowed you to take a laptop or your desktop and make it think like a server. So your laptop is still an S&P machine. It only has 1 memory controller. If you're testing code on your local machine, you never got the split NUMA nodes, so your query plans would always be interesting. You could turn soft NUMA on to force it to work that way. However, in SQL Server 2016, they released a new feature for soft NUMA. What happened was Intel's hardware has gotten so much faster now, especially for memory, your storage, and all this, and we're doing a lot more CPU processing, on workloads, and they found out is they are having ring buffer issues, which comes down to memory access problems, basically because the bus is being constrained. So Microsoft fixed that by what it does. So they actually create a logical NUMA node. So even though you might present 16 cores to it, Microsoft's going to take that 16 cores, and if it's one NUMA node, it's going to break it into 2 logical ones and break the memory in half and keep track of it that way. And it allows in the SQL Server scheduler OS basically takes care of that and makes sure you schedule locally. So vNUMA, this is basically the VMware part of it. It only comes into play when you've got 9 vCPUs or more. Every doc from VMware says greater than 8. I don't know why people like greater than 8, because you can't do 8.1. Just say 9. Because a lot of people I run into tell me that vNUMA comes into play at 8 vCPUs. It does not. It has to be 9. It has to be greater than 8. When you have hosts that still have 4 and 6 core processors inside of it, by default you're going to, and you run 8 vCPU machines, you're going to run into NUMA issues. You need to do a couple settings we'll come in later on to adjust. Which is actually the NUMA min vCPU. You change that to lower it down. So if you have a 6-core processor, you change that setting inside the host. You can also adjust at the VM level. And the great thing, vNUMA got introduced in 5.0, but it really got improved in 5.5, and in 6.0 and 6.5 are much, much better at it.
All right, so how did we go about testing? So we wanted to do some in-guest analysis. We wanted to look at memory usage of the host itself. So we went into ESX top. You press M for memory. From there, F to choose your fields, and then it's G for the NUMA fields that don't show by default. We've got some screenshots and stuff with that you'll see those fields and how to decode them. We did a lot of VMX file analysis. So if you change a setting of your VM, do you need to reboot it? Do you need to power cycle it? How does that affect it? We've ran into something very interesting around power cycling and the way that things are calculated. So what we did through our testing is we just kept resizing these VMs all along and just kept copies of those VMX out, and then used WinMerge to go and analyze what had changed when we were doing different things, and we found some pretty interesting findings. So we really kind of did a black box approach to this to just see, hey, how is it actually working? And then, back one.
Sorry.
And the important thing was, what's that worst case analysis? So this was a big one that really drove the session, because we were reading a lot of conflicting information out online, and it was, some of it was, hey, you know what, this stuff, the architecture is so new, it's really better technology, it's fast, and NUMA doesn't matter anymore. And so, that's strange, and this one says it does. And so there might be some testing that we can get to later that could lead you to believe that. But in our testing, there definitely is a penalty if you get it wrong. So the lab setup, I used an AMD server. It was a dual socket 16 core. This was nice because it gave us 4 NUMA nodes to work with. We had an Intel server. It was a 2x16 with 384 gigs RAM. Tintry for storage underneath. The SQL VMs were Win 2012 R2 plus SQL 2014. We've since done some testing on 2016 and both Windows and SQL. And the results on here, we left the screenshots to the other because the findings were all relevant and the same. The size varied for when we were doing different configs. Definitely the CPU and the memory. This is what we're getting into. And then we used HammerDB. HammerDB is a free tool you can get. It's a load generation tool. On the storage side, I absolutely do not like synthetic workloads. This is as close to not being synthetic as we can do without having real users and real data. It actually uses clients from afar, so we had 10 clients, many virtual users hitting across, so we were making sure we were making the boxes sweat from remote and not running in-guest processes that would otherwise conflict with SQL. And so we're going to determine how you can figure out your NUMA configuration from within Windows. One of the things we probably should have prefaced at the start here is a lot of the stuff in this are going to be little tiny tweaks and stuff. These are probably not your first go-to things if there's a performance problem. If you were to use a car analogy, we may be talking about things that's the aerodynamics of your mirrors and some little spoiler changes, how many degrees up or down. Pop the hood open first, check the oil, like all the basic stuff before you get into this. And then what we're trying to achieve is the Windows guest or Linux guest inside of a VM should think that it has hardware, that it looks a certain way, and when it optimizes to use that, we want to make sure that underneath that it's actually going to different NUMA banks and that we've got a match. And anytime you have a mismatch, here the guest thinks it's doing the right thing, it's going out of the way, and then the vSphere host might be penalizing it by sending it remote calls to the other bank of memory. So if you wanted to look at what NUMA looks like inside of Windows, you can go into your task manager and go to the performance tab and then right click and change your graph to NUMA nodes. This picture is just showing logical processors. And something to watch out for is down there here's a zoom on it, is the number of sockets that are seen by the Windows guest and the number of virtual processors. And so when we want NUMA to work right, remember it's 9 and above, unless we tweak it for special conditions. This is what we want to see. We've got 2 sockets and we're going to split between them. Well, we want to see this if our core count doesn't have enough to accommodate. Otherwise, we may just go with 1. And what we can see here, this is good. And if we move forward and take a look, so this is showing 2 NUMA nodes. So great, the presentation was done well. All of our findings around NUMA are all good. But if we look closely down here, we can see that our sockets says 16. So this is from a 16 by 1 configuration. So 16 sockets at 1 core each, which used to be our recommended practice for how to set up your VMs for everything to work automatically. And we'll get into a lot more detail on that. So this is not good. And and moving forward here, the other thing you can check is you can open the resource monitor down below. And in the resource monitor on the side, I usually change the view to small so I can see it all. You will see your CPU total, you will see your NUMA nodes, and then you will see each CPU and which node they're in. These should be all balanced well. But this is just another way to check on it. And this is just zoomed in a little more because it might be hard to see from the back.
So in SQL Server, you also make sure that SQL Server sees the same NUMA nodes or NUMA topology as the OS is seeing. So select star from OS memory clerks will tell you that. You notice I've got 5 things in here. This is a 4 NUMA node box. You start with 0 because they use cardinality for their cardinal or ordinal number. Number 64 is a special one from a SQL Server perspective. It's part of the remote DAC, or the DAC, the dedicated admin console, which is a way to get into a SQL Server if you have a runaway memory problem and you can't get in. It actually has some resources as a backdoor to let you get in as an admin to go kill a bad process, which shows up as an extra NUMA node. So if you only have 1 NUMA node, you look and you'll still see 2. If you have 2 NUMA nodes, you'll see 3. It'll be again 0, 1, and then 64. 64 is the DAC. The other thing I always look at too when I'm playing with SQL servers is the OS schedulers. This helps me understand what threads and processes inside of SQL Server are doing what things and what memory banks it's using. And it also helps me understand when I'm actually doing a NUMA spill or looking into remote memory calls.
So if we're looking in ESX top, we want to look at, so we're going on our ESX host, we want to look at ESX top. Again, I mentioned that you want to change to the memory view, F for fields, and then G to get those NUMA fields. And the fields that we care about, I hope I got a zoom on it, yep. Our NUMA home node is that first one. How much NUMA migration, your NUMA remote memory, and your NUMA local memory. Those 2 numbers should add up to be the total amount of memory. And then we can see a % locality on the side. So in the very top example here, for the VM called SQL HamDB01, we can see that it's using 2 NUMA nodes, and we've got 100% locality with memory. Now this is a bit of a gotcha because we have 2 NUMA nodes total on this host, and this one's spanning them, and we don't know which calls are actually going to which bank. So the fact that it touches all of them, this actually isn't that useful. Now it is useful for seeing what kind of load is on the different nodes and stuff. However, and what kind of balancing is there. And if you were to have a lot of remote memory, that's not a good thing. But ESX should be balancing this out for you. And if workloads change dynamically, then this is more likely you're going to get the remote because it starts to schedule on the other side and then slowly start to trickle that memory over. So anyway, the key point here is that percent locality is a bit of a false feel-good that everything's good.
And I just realized I forgot to add a slide to this deck because there is a perfmon counter to show you memory locality, to determine if you're actually doing it from the OS perspective, which should match, well, won't match this because again, this is per VM versus that's going to be by the nodes itself. All right, node balancing or node balancing. So basically, an imbalance occurs when you have a misconfiguration of some sort, i.e. you have more memory than the NUMA node has assigned to it, but you have less processors, or you've gone into a forced configuration incorrectly kind of stuff. Example of it basically, so we have a host with 2 sockets, 12 cores, and it's got 384 gig of memory. So each NUMA node is 12 cores and 192. So if I give one VM with 12 cores, it'll fit in a CPU side for one NUMA node, but with 256 gig of memory, it needs to be in both NUMA nodes. So what's going to happen is it's going to split and put half the workloads in one and half in the other. So I'm going to basically have a 6 and 6 and 128 and 128 for my memory pools. And that's considered an imbalance issue. If you can make that workload fit into 190. 3 to 4, yeah. If I make it 192 gig instead of 256, it'd fit in one single NUMA node, or it's time to really consider adding more memory to that box. So I can get to 512, so half would be 256, because you're going to get better performance inside a single NUMA node. The NUMApility. So basically, when a thread tries to schedule, the Windows OS and SQL Server, the scheduler OS there, actually will know where your memory is at and will try to always run your thread on a processor local to your memory. And it has the calculation to figure out when the thread pools are so backed up, is it faster to go to a free thread on a different NUMA node to get the memory for the NUMApility versus waiting an extra 2, 3, 4 cycles to go where the memory is local to. And we call it the NUMApility. So every time you have to wait longer to get a memory access, it is actually slowing down your processing. So in our testing, we did a contrived scenario, in which we'll walk through a bit later on. But you see, as we were going along, we're cranking on basically at 1.3 million transactions per second.
Per minute, yeah.
Per minute, sorry. And then we forced a 100% NUMA imbalance. Basically, we made sure everything was a remote call. We did it through bad hacks you should never ever do in production, just to show how bad it can be. And we went from 1.3 million down to 760,000, like that.
Small little disclaimer on this test here. Yes, we did that. We forced it to go remote for it. And the penalty wasn't all that bad. So to make it worse, what we needed was just a load on the other processor. So without a load on the other processor, it wasn't too bad because it could just turn around and serve it. So I think this was one of the ones online that we were trying to get to the bottom of is there a penalty or not? Because at first glance, it would look like, you know what, there really wasn't much of a penalty at all. But if you've got a busy ESX host and you've got processes running on that other socket, then your remote call's got to get in line behind all the other calls from the processor of all the other workloads. So this is where we got it, but workloads are going to vary. So HammerDB very specifically was 40%. Some are going to be worse than this, and some of them may not be as penalized.
Yeah, because again, this is probably the absolute worst case scenario of we forcing everything to go absolutely wrong that you could make go wrong. In real life, it should never happen. Exactly. Stop that. All right, VM sizing. So first of all, the best practices guide here is it's the 6.5. We updated it. Cool. I was going to say we had the 5.5 version still up there. So right size your workloads. As the VMware admins, right sizing is still the most important. And trying to fit a VM to a single NUMA node is very, very important if you can. Granted, there are many workloads that can't fit in there, and that's perfectly fine. But if you're on the borderline, use this to help convince your DBAs to right size and downsize to make it fit, because it will work a little bit better that way. But when you do have to go above that, they like to make sure your processes, your core counts or your vCPU counts match a multiples of your core counts. I.e., if you're in a 12-socket box, a 3 processor or 3 vCPU actually works sometimes better than a 4 vCPU. Actually, that's still dividable.
5. Better than a 5.
No one wants to do 5 though. But yeah, like on your 16s, 6 vCPUs doesn't work all that well compared to 8. Those kind of things. Or of course 24s and your multiples are above that too. And it makes the scheduler work better.
Yes.
Okay, so the question basically is why would an 8 vCPU not work on a 12-core processor? It will work just fine. However, the way the scheduler does, it tends to do, the CPU scheduler will like to line things up by size to some extent. And so when you're having one 8 vCPU machine, it's not going to schedule as efficiently. It's a small difference, it's not a huge thing, and if you don't have to, this is basically saying the absolute most efficient. It doesn't say it will not work, it doesn't say it'll cause you problems. It's just not the most efficient in terms of how the CPU scheduler works. Sure. Yes. Well, no, it's going to still fit, if it's a 12-core processor, it's going to fit in one NUMA node still. So it's not going to split across two NUMA nodes there.
But if your memory is greater than the memory that can hang off the bank of one socket, you're going to want to make sure that it does split across if it doesn't automatically do that.
And the 6.5 scheduler has gotten more relaxed to make it even less of an impact, to the point where we debated actually of taking this slide out completely, because your question is very, very valid. Why doesn't 8 vCPU work just fine? And the new scheduler has gotten better, and that it makes it less and less impactful. At 4, this is very impactful. In 6.5, it's a lot smaller.
So just before we move on, I'll give you a quick analogy that I love to use around CPU processing. Let's just think of our VMs, so let's think of our host as a restaurant. And if we have 32 cores available to us, no hyper-threading, but just 32 cores across 2 sockets, and we have VMs coming in. These are parties of 8, parties of 12, parties of 24 coming in. Now you get these little onesie twosies coming in, and they go right up to the bar. They don't wait, right? They eat and they get out. Now when you get somebody that's coming in, party for 32, here they are waiting, waiting for the entire restaurant to clear out, essentially. So we've parked it, we've got, okay, reserved it. Finally the last person's out. They all sit down to eat. One guy picks up a chip and says, oh, that's all I wanted, because they all got to come in together and get scheduled together. So, and then back in line and off it goes. So if you have very large vCPU count on even a single VM in a host, it can be very disruptive, and you will see ready time as a result of that. So that's the analogy I like to use. And then if you get into hyper-threading, the place where somebody can sit and eat a meal, how much work they can get done, it's sort of like you're sharing and sitting on laps at that point. So you're not going to consume any more food, but you can kind of schedule it a little faster. So if we go into, next slide, the virtual NUMA nodes. This is one of those examples. We go to ESX top, same thing. And this is an example of what bad looks like. So this is on a host that has, I believe that this one was two NUMA nodes on the host. And if we look here, I couldn't even get the field wide enough, but it looked like we had 24 NUMA nodes. And you'll see that our percent locality was still 100%. And so when we get into a situation like this, what's happening is that any effort in the guest to go and schedule the right place, this is just a free-for-all of single leaders in and out, not trying to keep that party together. So this is, let's click over. Yeah, no bueno.
So cores versus sockets. When you have the rules are going to basically be different if you have a homogeneous cluster or a heterogeneous cluster. It's more important to get your NUMA configurations correct than it is in most areas. So what we used to recommend was you make your VM 1 core per socket in many sockets. And that allowed VMware to configure NUMA correctly for you. The problem with that is it made a fraction of your L1, L2 cache from the OS perspective. I.e., when we showed you earlier, we had 16 sockets. Basically, you had NUMAs correct, but we had 16 sockets. The OS thinks we have 16 groups of L1 and L2 cache. When you're in a homogeneous environment where all your clusters, all the hosts in your clusters have the exact same processor inside of it, so the same amount of cores, you match your VM to your core count. To the physical hardware, i.e. it's a 2x12 box, you make your VMs fit the 2x12, i.e. 2x8, 2x whatever, and that'll work better. If you're in an environment where your hosts are different, some have 8-core CPUs, some have 12-core CPUs, some have 16-core CPUs, when you vMotion between the two, your NUMA topology on the hardware is different. You need the VM to be updated on it. So when you use one socket with many cores, with 1 core per socket mini sockets, and when you reboot that machine, you will go ahead and it'll recalculate the correct NUMA topology for the host you're on now.
And by reboot, we mean power cycle.
That's right.
And by power cycle, we mean only power cycle if you've applied the settings.
Which we'll get there pretty soon.
Yeah.
So the vSphere will, basically on first boot of the VM, it's going to figure out what is the best topology for you if you have 1 socket or many sockets, 1 core per socket. It's very hard to say that because 1 socket, blah, blah, blah. But yes, you want to talk about cores per socket, you want to have many sockets at 1 core each. VMware is going to go ahead and figure out what is the best configuration based upon the physical hardware on first boot. It will record that in the VMX file, and it will stay there until you make a change to the number of cores in the machine, or you reach power cycle, and we have a setting we have to set in a minute.
So the implications there is that if you've built a template for SQL, and you've built it off on a server over here, and you're deploying from that template, and you're keeping the vCPU size the same on that template, where this is going to remain fixed in there to match where that template was built, not where it's actually been deployed to.
Yeah, or you have a staging area that's 8 cores, and you move it to a 12-core processor box later on. And this is also actually only for 6.0 and below. We'll get to 6.5 in a few minutes. So when you change from 1 core per socket, basically, it's going to ignore VMware's, VMware is going to not auto-calculate. It's going to use what you tell it to. So if you wanted to do 4x4, and you on a 2-socket box, it's going to present 4 NUMA nodes to your Windows OS. Versus 2x8 versus 8x2. And if you do 8x2, that thing we had 24 cores basically was probably a 24x1. So we had 21 socket, 24 cores, showed up that way. So use multiple cores though when you want to need to save on licensing, because some people still have to pay by processor or socket for some applications. SQL Server's by core. So anywhere else though, if you still have to pay by socket, then you want to use fewer sockets and save on licensing costs. And if you're not sure of the underlying hardware, then go with the 1 core per socket, many sockets mentality, because that way VMware can figure out what's going on for you. And also, you feel free to change it if you desire a non-standard configuration. And there are some edge cases when you want non-standard, and we'll cover 1 or 2 of those later on.
Now, if you've got smaller VMs, I would recommend going 1 core per socket and leave hot add on and just kind of add to that. And that's all fine and good until you get up into where NUMA starts, which is right from 8, then you go on. And at that point, we don't want the hot add anymore, and we'll cover that too. But these recommendations, remember, are for large VMs that have NUMA applied to them.
And of course, results vary, test your workload. So, 6.5. You want to talk to this one?
Sure. So this is when we're talking cores per socket. This is where you adjust it. So if you are a real person, you might be using that that thick client in the background, unless you've gone to 6.5, in which case you're not touching it because you can't anymore. Then you are using this one or the HTML5 clients. And these are the settings we talk about. In the web client, you need to expand that, and we can see that this is 8 cores per socket for a total of 16 vCPUs, and that sockets is just calculated for you. And new in vSphere 6.5 is when we were auto-sizing that based on the fact that we had wide VMs that were many sockets in 1 core each. In 6.5, it will no matter what. So when you put something in here, it would hard code that. It's if you put 2 sockets and 8 cores, that's the NUMA node you would get. Now vSphere 6.5 will ignore that, calculate it for you, and try and put it on there, unless you want to go back to the old way where no, take it anyway, and it's right here. But what we're ultimately doing is we want to follow a green line config. So there's a URL at the bottom here. It's a blog by Mark Termachuk. I'll murder his last name, unfortunately. But super awesome, bright guy at VMware, and he's got some of these tables for different CPUs. So for the common CPUs out there, instead of kind of guessing, hey, how many do I put here and there, here it is. And ultimately, we're just getting down into where you get number of vCPUs required, 11, 13, 15. This is when we have to break out from fitting in a single socket to the other, and we don't want to have an imbalance. So if the number is greater, so in this example, this is 10 cores per socket. Once we get up and we have to span to 2 sockets, we don't want to do it so that we're imbalanced with one extra on one of them.
So what that means basically is in 6.5, the NUMA configuration is going to be done by default for you. And so doing your cores per socket will get you the right, basically, number of sockets presented to the OS, so your L1, L2 cache is not being fragmented. Versus back in 6.0 and before, you had to choose, if you're in a heterogeneous where you have different core counts, you had to choose between getting your socket view right for your cache fragmentation or your NUMA right. And getting NUMA right was more important than your cache correction. If you're heterogeneous or homogeneous where everything's the same, then you want it to be, you do your hardware matching. So more advanced settings. So the top one there, vCPU.
Hold on a second, we got a question?
Yeah, just a question. You mentioned something that was interesting. You said to enable CPU hot add. My understanding was, and maybe it changes, in the moment you enable that, you start paying a different penalty every time when you turn it on and you're not planning to use it. Like if I have a VM that's going to have that enabled, am I paying a tax for it? Every single VM that has that hot add enabled?
I'm not aware of any licensing that does that.
No.
But
From compute perspective.
okay.
Yeah, so the question is, when you enable hot add CPU, he says, is there any penalty to running that VM with hot add enabled? And I am not aware of any setting or any indication that's an issue. There is an issue we'll talk about later on in a couple slides, but that's not one. All right, advanced settings here. So NUMA vCPU max per virtual node. So span additional nodes. Basically, this is basically tell you when you need to split NUMA nodes. So in other words, this kind of matches your hardware. The next
for
one,
HT.
yeah,
false.
the next one, vCPU prefer HT equals false. We have a slide on this. The default is false, and leave it at default except for a few edge cases, which we'll have a slide like in 5 slides. Next one is the NUMA vCPU.min that equals 9. That's the default. That basically tells you when it's going to go have vNUMA. So if you're going to have a 6-core processors, you want to change this to 7. So your 7 vCPU machines or 8 vCPU machines would actually have NUMA exposed to them. Yes?
So is that still default 6.5?
Yes.
So if I physical core CPU, not talking about hypervisor, can I technically still change the minimum to say 15 or 16, and it wouldn't enable VMware?
Yes. So the question basically is, if you have a 20-core processor, and you happen to have, can you change this to say 16 so you wouldn't go to vNUMA until you get to 16? So the thing about that, so the answer is yes, but even though so vNUMA doesn't take effect to get 9 or more, the VMware will calculate what the proper NUMA topology is for you. And so even if you have 20-core processor and you had a 12-core VC or 12 vCPU machine, it will still split it in one NUMA node. It will not split it until you reach 21 because it can't fit it anymore. So you don't need to adjust it. You really only need to adjust that when you have smaller than 8 vCPU or smaller than 8 cores in your servers.
Question.
Yes.
How does that change for a low core, high memory VM? Do you have to therefore adjust it, or will
Low core, high memory.
machine and I have a 6-core VM, but I'm using a terabyte of memory? Is it going to split that for me automatically in 6.5, or I have to know?
It's going to split for you automatically in 6.5 based on your memory. So the question is basically, if you happen to have a lot of memory and a small core count, what will 6.5 do for your NUMA configuration? Because your memory is still greater than the size of a NUMA node, you'd have to present 2 NUMA nodes to give you the memory it needs.
Even if that value is set to 9 and I'm using 6 cores?
Yes.
Okay, good.
Question. There are a lot of knobs around the point that is very complicated. What are the ones typically you have to tune? I mean, just this one you said.
So the question is basically a lot of settings here we're talking about which ones we typically do. The typical answer for me is don't touch anything. It takes care of itself. It's only in edge cases, which we'll get into those.
We've also got the 2-minute version. Those were the ones that you would typically, we would suggest you just go and change. But otherwise, we want to show you where the knobs are to tune to get, again, what we want is that balance. How can you observe that balance, and what can you do about it? So we're showing you the knobs that you can turn, some recommendations around them, and which ones not to touch, which I believe are on the next slide after we follow this one here.
Yep. The guy in yellow back had a question?
Yeah.
Two questions. The first one is, does hardware setting matters? Because yes, it should be on or off.
So the question was, does hardware settings matter? We're talking about the VM hardware version? Oh, hyper-threading. We've got slides on hyper-threading that we'll cover.
Second question is, what happens if you do remotion? Now, different hosts might have different CPU.
We have a slide on that too. We'll get there. All right, so basically we'll finish blowing through the rest of these settings here. The auto size, once true, basically what that means is on first boot and only on first boot will it calculate that by default. So we recommend you change that to false so it'll recalculate it on every boot if you're going to be on different core counts on your hardware.
On a vMotion scenario, it's not going to change any of this on the fly. It's only going to be on a power cycle. So you're still exposed to that kind of imbalance that you're trying to avoid.
All right, so these are the ones look, don't touch. Oh, Rob, this is your slide.
Yeah, so this is, when we're looking at some stuff, how is it being calculated? And when we were, you can go into your configuration parameters. So this is where you go to a VM, you edit settings, and you go advanced, and you go down to configuration. There's a little button. And anytime you want to look at it, it's frustrating because when the VM is running, it's grayed out and doesn't let you look at the settings of it. So on your next maintenance window, maybe you can go in and look at it. Or you could jump into the VMX file directly, take a copy off it, and inspect it to see the exact same stuff. So if it's up and running, you actually can't get to see these things. But it is important to know what these are set to. So we've got these auto size settings here. These are not something that you would configure. These show up automatically once we cross certain thresholds. Like we go from 8 vCPUs to 9 vCPUs. This thing automatically shows up in there, those two lines, and it tells us topology about our underlying host underneath, and then when we should split up for the NUMA nodes. And I think I've got it clearer on another slide there. And so if I were to go in, again, if I can't get to that because my machine's running, well, go download your VMX from your data store and have a look at it. So when we were comparing these settings and we wanted to see this auto stuff show up, I wanted to know, hey, what's changing when I do things? I kept grabbing versions and versions of VMXs, make a change, and then I would look for differences. So here's where I found a difference. The VM names at the top, we have before power cycle, before power on and after power on. So I've changed it, and my VMX didn't change at all. And then I went and powered it on, and all of a sudden those things showed up, and it got calculated on the first boot. And that auto size cookie that you're seeing is going to be, that first part is going to be the number of cores that are in the entire server. And the second number, that 1, is always 1. I'm not quite sure why. It doesn't seem to matter how many sockets we have, but I could not find an example where it was not 1, and I could not find it documented, although it might be there. But through trial and error, I was able to deduce what was happening with those first numbers. And then on the second side here on the right, with our NUMA auto size vCPU max per virtual node, this is saying when to go and split and do not put more than this many of cores inside of a NUMA node. And so this is where, if in this case, we've got 24 cores total across 2 sockets. When we hit 12, go over that and make sure you split it into NUMA nodes. And so then, just for fun with those VMX files, I pulled them all out. This is the AMD system that I was working with because it had 4 NUMA nodes. And so what happens when I add? So I start at 9 sockets. Cores are all 1 down here. And I went all the way up to the 32 that were available, the logical cores that are available across that VM. And I could see that max per node would change until it went to split. And as we added 1 socket at a time, power cycle it, calculate it, keep going, I could see it went in cores on the right side, socket 0, socket 1, socket 2, socket 3, and when it decided to start to populate those. So the preference is to fill up as much in a core as possible, or sorry, in a socket as possible before you go and you split. And some of these, as you notice, being imbalanced, not having even the same numbers in all of them, would not appear on that green line config. Those would be yellow lines there.
So hot add gotchas. So when you turn on hot add CPU, it will disable VNUMA. So if you happen to have it on a machine that's got 12 vCPUs in it, it's not going to have it. So what happens is the machine's going to schedule. The Windows OS doesn't know there's NUMA underlying it, so the VSX is still going to use NUMA because it has to, but it won't be able to optimize the threads to be on the right memory. So, and basically, if you're going to have a large virtual machine, you need to turn off hot add CPU. Hot add memory works perfectly fine, except for one small caveat. What the caveat basically is in the 6.0 it changed? Yeah. So in 5.5 and below, all the memory was added to NUMA node 0. So if you happen to have 256 and you went up to 384, you added 128 gig of memory, you have 2 NUMA nodes now with one 256 and one with 128. It'll stay that way until you power cycle. In 6.0 and beyond, when you add that 128, basically now you have it split in half and you've got 192 and 192 and it adds it properly. So that's the only gotcha there. And then it's actually based upon hardware version, not actually on ESXi version. So if you upgrade to the latest 6.0 to get this function, you also need to upgrade to hardware version 11 or 13 with 6.5 now.
And so the hardware version is as simple as right-clicking that VM, saying upgrade hardware version. But it's got to be powered off. So it does take a little downtime hit for that, but worthwhile to get the most out of what the platform can offer.
Okay. So when you vMotion a VM that's got VNUMA enabled on it and it's working and using it and spanning, what happens when you move between hosts that have different CPU counts and processors? So say we're going to use a 12 vCPU machine that's going to fit into a single NUMA node where it's at. I vMotion it over to a host that's got 20 cores per socket. I move it over, it still fits inside of a NUMA node, nothing happens. I now move it to an 8 vCPU machine or host, and what's going to happen now, it has to split the thing up. Since it's properly divisible, it's going to now make 2 NUMA nodes. The problem is the OS doesn't see it originally because the OS can't recompile an NUMA configuration on the fly. But so you're going to have a memory schedule issue. When you reboot, it's going to be, if that auto size cookie, like auto size once was set to false, it's going to correct itself. But in the meantime, you're going to be in a NUMA imbalance. The OS will still work, CPU, SQL will still work, everything's going to be fine. It's just you may be a little bit slower. You may be incurring NUMA penalties. Again, those 2 settings, how those set will help you resolve that when you power, so your next power cycle.
And question up front.
No.
What happens in a cluster where you have EVC enabled, but the core counts are the same, but the feature sets are different?
Well, with EVC, the feature sets
the question is,
yeah.
what happens in a cluster if you have EVC enabled and core counts are different, but your processor families are all the same?
Core counts are the same.
Core counts are same, but your families are different.
The EVC mode is going to mask the instruction set, so you're on the same processor family, so it'll work just fine. In that case, you're going to be considered because EVC is there, you're still going to be considered a homogeneous cluster.
My question.
Yes.
Your settings there, are those applied only to 6.5 or is that across all of them?
That's all process. So the question is all the settings listed, the NUMA auto size true, NUMA size all false. That applies to all of them. Actually in 6.5, one of them goes away, the
Auto size true is deprecated. It doesn't show up as a line item anymore. It's there and it's set to true.
No, it's going to be messed up still. The question was if I move off to a host that messes it up and I move it back, what happens? It's still messed up. You got to power cycle it. All right, prefer HT. So prefer HT is a setting to tell if you want to prefer to use hyper-threaded threads or not. It has nothing to do with hyper-threading at the host level. You want hyper-threading enabled. Some people think prefer HT means it exposes hyper-threading to the VM. No, it does not. Prefer HT means have the ESXi scheduler think of hyper-threaded cores as ones to use for it. So if you have a 8 core box and I've got a 10 vCPU machine, if I use prefer HT, it can schedule all 10 threads on that 8 cores, and I'll stay inside of one NUMA node. In most cases, so the default answer from VMware is they turn it off. In nearly every case, that is the right answer. A few edge cases where you want to have the advantage of being in one NUMA node is greater than the lack of processing power because you only have a small bump from using hyper-threading. You don't get an extra full processor. You only get between a 20 and 25% performance bump on that. The edge case basically is if you happen to have a lot of inter-cache communication. So in other words, you're doing a lot of calculations of small amounts of memory that stay in the L1 and L2 cache at the processor level. Having things in the same NUMA node will go faster because I don't have to have it loaded in 2 pieces of cache. And it's a very small edge case, and I rarely see it happen.
Synthetics would probably be where that would happen, where you don't have real data and you have not enough change of data, and you're just firing these little ones and zeros back at it, and they all fit in. Would be
correct.
Cold.
And so we're starting running a little bit short in time, so we're going to hold all questions from now until we get through the deck and then have some at the end, just because I want to make sure we get through the rest of the slides more than anything else. End of the day, if you want to turn this on, you need to be able to test your workload properly. And that was not a synthetic workload. You need to actually test your real life workload to make sure it will work. Otherwise, you may be turning it for no reason or impacting yourself. NUMA host density settings. So these are the areas where I tell people never ever touch unless you're on the phone with VMware, and the VMware technician, usually level 2 or 3, has said, go ahead and let's make some changes on it. This affects how the host does NUMA scheduling for each VM. I.e., when a VM is first powered on, it is moved on to it selects, and if it's in a NUMA node, it decides what NUMA node it goes on to. So you power on 20 VMs, and you got 10 go on one NUMA node, 10 go on the other NUMA node. Oh, we didn't need half of these, they're VDIs, we turned them all off, and it'll bounce them back and forth. So in other words, I have 10 over here and none over here now, it'll move 5 of these over. On larger machines, what happens though is the CPU scheduling of that will jump instantaneously. The memory will not go over. The memory will stay. So if I happen to have an 8 vCPU machine and it had, like, say, 64 gig of memory, it had an internal host level imbalance of NUMA, it can move that VM over. All memory will be remote at first until, as new pages get read in the memory, be read over here. It will slowly trickle it over. The reason why I did that is if they try to copy it instantaneously with it as fast as they can, they would saturate the QPI links, and every VM on that host would be punished, not just the one that they got moved over. You can tune that in here, but don't. There's a few other edge cases inside there with all it does this. So in other words, at the end of the day, don't ever change these unless you're talking to VMware on it, because it can change a lot of, most likely it's going to have impacts that you don't understand because it's not well documented, and most people don't understand fully how it works and what it's going to do for you. NUMA and BIOS. So hardware manufacturers call things differently. And in the Westmere slash, what was before Sandy Bridge? What was Westmere? No, Sandy, whatever. Ivy Bridge, that was after though, so before I thought. I went backwards. But so hardware manufacturers, some of them have had NUMA turned off by default, some had NUMA nodes turned on, NUMA turned on by default. Today, all of them have it turned on by default, so you buy a brand new server, don't have to worry about it. They also have different names for it. Some call it NUMA, some call it node interleaving. One of them says node interleaving, and they have it on by default because they think you want to interleave things. Node interleaving means I'm making all my memory the same, and I'm actually creating what I call a SUMA, which is simulated uniform memory access, which is I'm making everything equally slow, not something's fast, something's slow. So in most cases you want NUMA on or node interleaving turned off. Check with your hardware, your manufacturers, or beat up in your VAR, because that's what they're for.
So before we blame NUMA, we had some pretty interesting results in the tests. And while we're running this HammerDB, we've got millions of transactions per minute flying across, and we're tuning this, and we're adjusting that, and now we're moving. We were imposing penalty this way, that, and I'm watching the graph go up and down and up and down, and then they fell through the floor. My performance absolutely sucked. It was orders of magnitudes worse, and I went from 1.25 transactions per minute down to under 1,000 transactions per minute. And I kind of scratched my head, and I wanted to figure this out. And even when I put all my NUMA settings back, it didn't make a difference, and the performance was awful. So I said, Sean, I don't get this. What's happening? Well, let's take a look. So HammerDB, what it's doing is it goes in and it's changing this database. And when we grew from the original 200 gigs and we started writing in and out and changing things, this database grew up to about 245 gigs. And somewhere around that point, this is when the performance fell right through the floor.
And the short version from a database perspective was the amount of data changed. The index and stats were now outdated enough. It was having to do a table scan instead of an index seek. And all of a sudden, performance went through the roof, or through the floor, because of how the plan executed. If we did, so what we did, we just did some index maintenance and the stats update, and the problems got all fixed.
So one of the signs of that is the I/O went way up on reads because it was scanning through the table again and again and again. And SQL said, hey, do this all the time. It's not worth looking at the index. It's too old. Change to this kind of mode, and we're penalized. So, if you have a problem and someone just gives you a random script, of course you run it on your SQL. So Sean gave me a query, just double click it, here we go, and I just wait. And it started grinding away, and I think it was about 50 minutes, just shy of an hour. And then when I was done, I said, John, what did you do to me? My database is 375 gigs now, and it just inflated the thing. Well, he had built indexes for all the different, for all my different columns, and
we adjusted some fill factors and all kinds of internal database stuff, which for the infrastructure folks, nothing that important. But the result of it is, it wasn't a NUMA issue; it was a SQL Server issue. So make sure you check all your normal things before you go down some pipes.
So don't use a big infrastructure overkill hammer here when it's just as simple as maybe indexing on the weekends.
I.e., in other words, also, if things are running fine today, tomorrow it's not a NUMA issue, it's something else. Look at those things first. Your NUMA settings should only really, only on your large SQL Server VMs, and only you need to tune them in certain edge cases. Most of the time it's done correctly. Here you drive. Sure. Fast.
Thank you. All right, so got some screenshots here. These are from Tintri VM Store UI. That's the tool that I have available to me. I've got my per VM view, so this is a SQL Server at the top. This is what happens when I'm running my HammerDB in autopilot mode. And what I'm doing is I'm stepping up the number of virtual users hitting the database, and I'm doing it over time, and we can see that in the top graph, those are IOPS, those are, the little haze above it is kind of a normalized to 8K, just to an apples to apples meter of sorts. And what we can see is that it kind of went up and up and up, and down on the bottom, so we get diminishing returns. At some point we throw more at it, and it's just too busy trying to do things that doesn't actually get as much work done. Down at the bottom, what we see is that when that happened, we had host latency creep in. So we measure the latency coming out from the VM through the hypervisor, all the way through the network, and we show you that visualization for all your VMs and all your vDisks all the time. And so we could actually see a byproduct of that. So the significance here is that in order to get max performance in our setup, we need to do an autopilot to know, with all the clients we had and the server config we had, where's our sweet spot to get the best performance in the first place. And once we threw too much on, then our performance started to degrade because we're just over scheduling too many threads, and we're just overwhelming it. This screenshot here, do I have it? Yeah. This is what happens when you have that virtual NUMA that I showed earlier, which is a bad thing, and we can see the resulting drop in performance. So we were driving along, and we went down. The last metric there was 1.245 million transactions per minute. Here's a hit as we go through. This is one where we've got a server running with the home nodes, and there's 4 nodes in this box. We're using 2 of them, and we are hitting some. Yeah, that's a little bigger. We are using one VM to penalize one of those nodes so that we could see the impact of that as well. This is where we're actually doing the hey doc, it hurts when I do this stuff. We're going into the advanced CPU, and we're scheduling the affinity to actually pick which cores we want to run on. I would typically not do this, but this is where we want to do it because we want it to enforce it a certain way. We had a tough time making it go bad because ESX kept doing the right thing and correcting automatically for us, which made for pretty poor results. Well, good performance, poor presentation. We did the same thing on memory, which nodes we could use it from, so we could schedule the VM that we're testing and also that VM that's sitting on the remote node. This is that autopilot setting. And in the background, we had results from every time it ran. And then we go through and we find the TPM and the NOPM, which was the new orders per minute, that were best results. And in this case, it was 312. This is just for tuning HammerDB if you wanted to do this on your own. We've got 40 seconds here, HammerDB clients. This is just as we kept running things at it. CPU up more and more and more, throw it at the database. We wanted to make sure we were saturating the database, but at the best performance without actually overwhelming it.
And so closing comments, basically, when in doubt, don't touch it. When you think you understand it, it's probably when you're in a danger zone, which you can make things better or even worse. I've seen it done wrong more than I see it right, but so again, we don't tinker with these settings until we need to, and then it only applies to your truly large, high-performance SQL servers. So all your small ones, don't worry about it, don't think about it. They want us to clear out the room fairly quickly. Rob and I will be out in the hallway answering all the questions you want to afterwards because of their session. And thank you for your time.
Please fill out your surveys. We appreciate your feedback, and we can work on making this more and more.